So the major limitation with that Bohr model is it's two-dimensional. Yes, it represents electrons as moving on waves, but they're still on the flat plane. They're still 2D, and the world is not two-dimensional. We need a model that gives us a three-dimensional representation. So we're going to talk today about the wave mechanical model, also called the quantum mechanical model. It is a mathematical model, but the math is far beyond me anymore. I took a one-semester class on the math just to draw the shapes and the pictures that we're going to talk about today. We're not going to do the math. We're going to look at the pretty pictures the math makes. So it's kind of like saying, I'm not going to show you the equation for the circle. Here's the circle. You know, we're going to look at it from that perspective. What's the output? But the difference, there's two big differences between these two models. One was that the Bohr model just had electrons on energy levels, and they were represented by circles of electrons. The other was that it was 2D. This is going to be 3D. But in order to get it to 3D, we're going to take these energy levels and break them up into smaller and smaller locations, into sublevels, and then even further down into orbitals. This model is considered to be a 90% accurate or 95% probability. So if I told you where an electron was supposed to be, there's a 95% chance of finding it there. Why isn't it there the whole time? Sometimes it goes to Fairfax and comes back. So it's kind of like that analogy we had in the beginning. If we describe the location of a person by where they live, we might be right most of the time, 95% of the time. Electrons are pretty hard to pin down. Why are electrons really hard to pin down as to their location? They're going so fast. Let's write that down. Their velocity is very fast. They're very small. That's good. The problem with something that's moving really fast is by the time you point at it, it's gone. And if you've ever watched NASCAR for even 5 seconds on TV, or if you've gone to it, you probably know this even better than I would. By the second you look at the car, it's gone. It's moving like 300 miles an hour or something. I don't know. I don't watch NASCAR, so couldn't really tell you. But the velocity is so fast, it's nearly impossible to nail down the position of the car. And that's at hundreds of miles per hour. Electrons move at about 10 to the 6th meters per second around the nucleus. That velocity is so fast, is it possible to nail down the exact position? No. This is an idea that a guy named Heisenberg came up with, the Heisenberg uncertainty principle. He says the faster something is moving, the less you can know about its position. And the opposite's true. If you know its position, you don't know its velocity. So let's say we were watching NASCAR and we pause the show. We could say, hey, the car is right there. If you know where it is and you don't have access to the dials or the gizmos inside the car, can you tell how fast it's going? No. If you were running down the track and I just took a picture of you and I'd look at the picture later, I would have no idea how fast she was running. I would know where she was when I took the picture, but I wouldn't know anything else. Electrons are even harder to pin down because the only way to see an electron is to hit it with a photon. And when it hits with the light, the photons are light. When it hits with the light, you're actually kind of move its position. It'd be kind of like if I was running across the track and I knew where you were because I bounced into you. But after I bounced into her, I wouldn't know where she was anymore. She'd be going off in a new direction. I'd actually be impacting her position. So Heisenberg says this. So these guys, a whole group of guys, comes up with this mathematical model. Let me write some of their names down here. Their names are Planck. Let's see. Schrodinger. And Schrodinger's the one who's the equation is named after. It's called the Schrodinger equation. De Broglie. Heisenberg works with these guys. There's one more I'm missing. This one helps him a little bit. Oops, let me try to write that correctly. This guy helps a little bit. He doesn't do a great deal. He's kind of busy with other math. And he's a contributor to this idea too. Yeah? Schrodinger's the one about the Schrodinger's cat. Is it in the box or isn't in the box? You don't know what's in the box. Yeah. You can't open the box without knowing. Yeah. That's actually the same concept. Is you don't know where the electron is until you hit it with the photon. But by the time you hit it with the photon, you don't know where it is. So I can't really remember how that joke goes there. I'm recording all of this. Yeah. It's like, what's the idea behind that? There's a cat in a box, and you don't know if it's dead or not or something? I can't remember. All of you just mumbled the same answer. I have no idea. It was like, what was the statement? What did you say?
Like, you don't know, like, the cat is still dead and alive until you open the box, and once you opens up the
Yes. So there's two possibilities. The cat be alive in the box. Cat could be dead in the box. And until you open the box, it could be either. When you open the box, then suddenly reality presents itself, right? That actually is directly related to what we talk about with electrons and spinning. Electrons could be moving one way or they could be moving the other, and you don't know until you hit it. And then after that, you've messed with it, and it's no longer the same. You know what the answer to that question is, though? Just shake the box. Cat will let you know if it's alive if you shake it. If it's not, it won't do anything. Unless it's I guess it could be a mute cat. It's a horrible idea, Joe. Why'd you say that? Oh, it was recording all that. That's great. Thanks, guys. Energy levels. So unlike the wave mechanical model, unlike Bohr model, we're going to split this up into three areas. There's the energy levels, just like before. This is kind of equatable to the distance from the nucleus. So when somebody says to me that an electron is on the 4th energy level or an electron is on the 7th energy level, in my mind I've always imagined that's a distance from the nucleus. It's more energy, it's farther from the nucleus, it's less energy, it's closer to the nucleus. And then the sublevels, this is where we start to break them apart. We're going to say there's different locations or different areas we might find the electron. But since it's on the same energy level, they have just about the same amount of energy. And then we're going to whittle that down even further into orbitals. Orbitals are a much more precise location. And then what gets kind of weird is the shape of the orbital, the actual shape of where we think the electron is, depends on what type of sublevel it's in. And so we're going to say that there's 4 types of sublevels. There's S's, P's, D's, and F's. S's, P's, D's, and F's. In which sublevel it's in really depends on how much energy it has, how far it is from the nucleus, and a whole lot of other issues. But for us, it's not too bad. We're not going to have to calculate all those things. We're going to have to use a certain set order, and I need you guys to get out the periodic table you have from me and flip it to the back. If you need to borrow a periodic table, I can give you one. So we are going to use what's called Aufbau's order to figure out where electrons are around the nucleus. Before we do that, we kind of have to dissect what these numbers mean on there. So let me zoom in here. I'm going to zoom in a little closer. That's not good enough yet. So let's look at this one first. The one is the energy level. And feel free to write on the back of your periodic table and kind of diagram out what this means. The 1 is the energy level. What would this 2 be then? That's also the energy level. And the 3, energy level. So those coefficients are the energy levels. And in my mind, I kind of think that tells me how far away is it from the nucleus? How close is it to the nucleus? If it's on the 4th or 5th or 6th or 7th energy level, you're getting farther and farther and farther away from the nucleus. You got me what the coefficients mean? Kind of describe how far away. The S's, P's, D's, and F's, these are our sublevels, and they have a couple of set shapes. Very set shapes. And in your notes, you have some axes we're going to draw on. And let me just insert a blank page here. Insert page after. And so what we're going to do is we're going to draw a 1s, then we're going to draw a 2s, and then we're going to draw a 3s. Do you see where that is in your notes? Now, what do those coefficients mean? 1, 2, and 3? The energy level. So this one is the lowest energy level for these three. This one's the highest energy level for these three. And I said it's kind of like distance. Well, when the wave mechanical model was being used and all the math was being done that we don't have to do, this S sublevel turns out to look like a sphere, if you can spell sphere. And so I'm going to draw a small ball, a small sphere. That's on the first energy level. The second energy is farther away. What should I do with the second one then? Make it bigger. I know that's slightly eggish. What about the third energy level? Even bigger. Wow. And I know that just looks like a circle. I'm not going to try to be like, look, it goes forward and it goes back. And then I'm not going to try to make it look 3D because I can't do that very well. I don't have a three-dimensional Promethean board yet. But these should be three-dimensional spheres. First energy level, tight, small ball. What's in the middle of the small ball? The nucleus would be right there in the middle, right? And that's not the middle. That's quite off-center. Let's say here's the we'll make it black there. There we go. Nucleus, nucleus, nucleus. So anytime we talk about s orbitals or s sublevels, we're saying that the electrons are moving around on a sphere. So you could kind of think like if you were tracing your finger on the outside of a basketball and just slowly moving your finger around, and you kept moving it around, what would you slowly trace out if you kept moving your finger around? You would eventually trace an entire sphere. Well, the electron's moving around, and eventually, as it moves around, it traces out a sphere-like shape. So it's not the electron's a sphere, it's moving around in a spherical shape. Does that make sense? So we're not going for circles anymore like the Bohr model. It's actually got three-dimensional shape, which makes a little bit more sense because we live in a three-dimensional world. So this should be some sort of three-dimensional shape. Now below that, you have four axes, don't you? Let's do the first three. That's like perfect. That's crazy. Once I mentioned it, I couldn't do it again. And the next set of orbitals are the p's, right? This is px or py, or what does it say? Px. This one say py? And this one says pz. Whoa, what is the pz going to be on? These p orbitals or p sublevels are not going to be spheres like the s orbitals. They're going to be more of a peanut shape. Let me change colors here. Does that kind of look like a peanut? But I like to say peanut because this should not be looking like a number 8. It should be three-dimensional and occupy space. A three-dimensional shape. And the reason it gets skinny here in the middle is because at the same time you'd have this p guy going on, you would have one of these s orbitals. And that s orbital would be taking the space in the middle it would push the electrons away from it. And so they'd get real close to occupying the same space. What would the py one look like? It'd be up and down. We're going to do it like that. We're not going to do it like the math people do. When they do a three-dimensional axis, they do, I don't know if you've seen this, they'll do x here, y there, and z is up and down because they flip the plane around. And then the z-axis should be doing what? Coming out at you. Woo! I'm really big because I'm coming at you. I'm really tiny because I'm in the background. So it should be sticking out of the board and going back into the board. But since we don't have a three-dimensional Promethean board and none of you are wearing your 3D glasses today, we can't see that it's sticking out of the board. But trust me, it's like way out here. All right? So these three shapes all occur at the same time. And so we could also take these three shapes and put them on one axis, and say we have one on the y, one on the x, one on the z. And I try to make it look 3D, but I'm not the best 3D artist ever. I'm going to actually try to delete that so that looks like it's in the front. So it's kind of sticking out of the board. One demonstration that sometimes works for people is with meter sticks. You juggle the meter. No. Here we go. What axes did I just create? All right. Got a three-dimensional axis. Now imagine that there was a ball or an electron on the tip. What shape am I carving out with the meter stick right now? No, like the whole shape. Like go down the length too. I'm making the peanut. Now I don't have like a ball on the end, so it's not rounded at the edge. So just, don't expect too much. They're just meter sticks. And then you can do the same thing here, right? And as this one goes like that, it gets close to this one that's doing that, doesn't it? Like they get close there and then they move away. And they get close and they move away as they're going around. And so the reason they don't touch is why? What are in these shapes? Electrons. What do electrons do to each other? Repel. So as they get close, they go, no, go away. Go away. And they start to move around in the three-dimensional axes, and it really gets complicated after a while. So we just put these away before somebody gets hurt. That would be me. And so we could have all three, but eventually run out of space. And if you run out of space and you can't put any more electrons around the nucleus, you have to go farther from the nucleus. So we have to go to a new energy level. And so Aufbau's order, this order we have here, helps us figure out how to put the electrons in order. First energy level, it's an S, so what shape is it? It's a sphere. And then this superscript, don't say squared, that means, that's an eraser. That means 2 electrons here. Means there's 2 electrons there. That's a number 2. You haven't seen one before. And you can only put 2 electrons on the first energy level. What if you have a big atom? Well, then you're going to have electrons on multiple energy levels. So we're going to do a really small configuration. We're going to write out a smaller element. We're going to do argon. And somebody find argon on the periodic table and tell me how many electrons it has. Ooh, look at all the periodic tables flipping over. 18, 18, 18, 18. Right? It's number 18. Therefore, 18 electrons. So what we're going to do is we're going to write down where these electrons are. And this is called an electron configuration. We would say, well, I could put 2 electrons on the first energy level in a sphere. Or they'd move around and make a sphere. But if I have more than 2 electrons, I need to use more energy levels. So where do the next set of electrons go? To the second energy level. So you go to the second energy level, and there's another sphere that's somewhat bigger, and it can hold 2 electrons. And then there's a second energy level with p's, and if you remember, there's actually 3 shapes, and each one could hold an electron. It can move back and forth. There's the electron moving back and forth. But actually, you could have 2 in there at the same time. And as long as they didn't really run into each other, they're fine. And so if there's 3 shapes and they can each hold 2, we can put a total of 6 in there. Have I taken care of my 18 electrons yet? Let's do the math. 2 plus 2 is plus 6. We're done, right? No. We have 8 more to go. But there's no more space on this energy level. What should we do? Go to the next energy level. So, we're going to say 3s2. Are we done? What else should we do? What's after 3s2? Yeah, we did 3p6. So let's add it up now. 2 plus 2 plus 6 plus 2 plus 6 is 18. Did you guys write that down? Because I want to show you what that would look like. So here's a big axis, and this drawing is going to be horrible. And I will never ask you to do a drawing like this. On the 1s, what does a 1s look like? A small sphere. What does the 2s look like? A bigger sphere that is surrounding the smaller sphere. What's after the 2s that you wrote down? 2p's, and then we'd have one on the y-axis, one on the x-axis, one coming out of the board, and one dropping back into it. And we're done, right? What's left? Did we get it all? Oh, no, there's more. Darn it. Change colors to go red. A 3s, which should be a bigger sphere, not circle, sphere. Remember, it's 3-dimensional. It actually goes back here too, and it comes up here, and it's got volume. And now we're done, right? What's left? The 3. Oh, so I should make bigger. Going back in space, coming forward. So what we're doing is we're kind of leaving people a map. It'd be like if I told Claire, it's like paint by numbers. I want you to put the electrons in the following location. Go draw this. I will never ask you to draw it, but I might ask you to do this. And that's called an electron configuration. Just writing down where are the electrons. Do you have off-Bose order? Yeah. It's on the back of your periodic table. You get to use it like always. Okay? You don't have to memorize the order. It is actually hidden on the front side of the periodic table, but it's not blatantly obvious. I'll point it out at a later time. But what did we not talk about that's on off-Bose order when you were looking at it? There's arrows, aren't there? Why are there arrows? Well, because off-Bose order actually fixes the order. Originally, these guys thought you just went 1s, 2s, 2p, 3s, 3p, 3d. And they believed you would just go in perfect order. And that's how it works if you're dealing with just hydrogen in one electron at a time. But once you start to have multiple electrons, it gets thrown off. The order is off. So I'll say that off-Bose order makes the order a little off. It's off-Bose order, so it's a little off. And it really gets wonky, but it's kind of like a game of chutes and ladders. Remember chutes and ladders? You'd go up, and you'd almost reach the end, and then you'd get on the slide, and you'd be like, oh, come on. And you'd slide down, and your parents would cheat. They made you go all the way down the slide, and then you had to go your way back up. Oh, there's another slide. That's how this works. We're going to do a more complicated one. We'll do bromine. Somebody tell me how many electrons bromine has. It's Br. 35. 35 electrons. Now the good news, it always starts the same. You always start here. So we always start off with 1s2. Now what comes next? Well, go down the next diagonal. 2s2. So far, it's not any different. Go to the next diagonal and slowly slide through and pick up the pieces as you go. 2p6, 3s2. Then you go to the next diagonal. 3p6. And here's where it gets difficult. Keep going down the diagonal. You gotta finish the arrow. You can't just like jump off the arrow. If you've ever tried that on a water slide, you're crazy. You got to keep going down the arrow, and what do you hit after 3p6? 4s2. And here's where it's slightly off. And so there's a weird spot that occurs there, and the 4s gets filled up before the next piece. Did we finish this arrow? So we got to go to the next one, and what's the next piece we would write down? 3d10. And there, we finally picked up the 3Ds. And so what happens, if I can use my hands to kind of describe this, is we have a small sphere, then we have a bigger sphere. Then we have these balloony shapes. Then we have a bigger sphere. Then we have bigger balloony shapes. And then it skips to a much bigger sphere. Okay? Skips to a much bigger sphere before it comes back and fills in the little space that's available for these d orbitals. Did we get to 35? No, we're 2 plus 2 plus 6 plus 2 plus 6 plus 2 plus 10 is 30. So we're a little bit short. We haven't quite gotten there. Keep going down the slide. What comes after 3d10? 4p6. Wait a minute. If I write a 6, that would be 36. How could I solve this? Make it a 5. This is the maximum I could put in there. It fills up at p6. But if I have only 5, just don't fill it. You know? Just write a 5. So you have a p orbital that's got electrons moving around it. You got a p orbital that's got electrons moving around it. And you got a third p orbital, but it only has one electron. It's not filled. So it's just slightly filled. Okay? Let's see what else we can work out here. So most of your homework, if you look at worksheet 1, is like, converting wavelength into frequency or frequency into wavelength. And then there are a bunch of write the electron configurations. This is using Aufbau's order. We got a couple more minutes. We'll see how far we get, but we're not going to get enough that you can do all of that homework, but we're going to get pretty far.